the chapter in Eitan's book on drift. Yeah, so I'm happy to hear, there we go. If people have any comments as I go along, or particularly if you think that and I'll be like kind of skimming it, but if you think that anything is presented that might not be self-contained, like maybe something's like too complicated. Throughout the book, we tried to insert some references. You know, again, this isn't like meant to be like a statistics or machine learning full theoretical book, but here and there we like insert some references to like say bootstrapping or things like that, or hypothesis testing. If you know if someone needs more background on something. So it's not completely self-contained, but I tried to, for the most part, to explain the things that are like directly relevant. So if there's anything maybe that you think that could be better explained, or any comments at all will be helpful. Okay, so just the basic outline of the chapter is talk first about drift in general, and then we have a few papers that we've published that kind of use drift in different forms, which I kind of mention. I might skip that here. Okay, I don't really know what I'll have time for, and then I kind of go through statistical tests and the various kinds of ways you can analyze drift, and kind of like a primer for mostly statistical tests that are two sample, like telling whether some data is drifted drifted relative to another data. And that's particularly useful in drift because we're trying to decide if something's changed, so we have some kind of baseline and then future data. Okay, so the basic idea is drift is some kind of change in data set, either in the data set itself or in the performance, say, of a machine learning model that's been applied on type of the data set. So on top of the data set. So I can discuss both of these scenarios. The first thing is kind of just to define conceptually what drift is. So, Eitan, by the way, do you think? Can you let me know like what I should cover?
Um,
Is this fine
yeah,
or?
it's fine. Keep going.
Okay.
Don't skip anything. Just go slowly. We'll do it more than one time. Don't worry.
Okay, fair enough. Okay, so starting off, we have some kind of X is these input data, and it may be multivariate, in which case we have these are each columns. And then you might have a Y, which is some kind of target feature. And if you have a machine learning model, you're trying to predict the Y from the X's. So maybe it's a classifier or type of regressor. And here I use probability distributions just in an abstract sense, to say like a model would be, for example, what's the distribution of Y given X? Like we're trying to predict uh, uh, the target feature based on X. It's unobserved, but it's like a theoretical thing. But when we make a classifier, we train a classifier, we're kind of like trying to estimate what this distribution is. So we never actually usually see this. You see the estimate of it in the model. Sorry, in the data set that is given. So okay, so the joint distribution again, because you usually have a target feature and the X are observed together. That's the joint distribution. And again, this is just in an abstract sense. And again, there's no like really parametric stuff here. And you can decompose this just by the conditioning. Either it's the distribution of Y given X times the probability of X, or you can also decompose it the reverse. You can say that it's the distribution of y times the distribution of x given y. So you can decompose it either way. The idea is basically if you want to say that this joint distribution changes, it's enough to say that either these, however you choose to decompose it, either of those have changed, and you have two samples, so either of those components have changed. So for example, if I have this different distribution p prime, and there's different values of x and y, if that's different from this original distribution, then either the data distribution has changed, or the model, which is like the relationship between y and x, has changed between the two data sets. So here's kind of the illustrative example. So basically okay, yeah. So x here is a bivariate, basically two features. And you can, a point is the location of like a value of x is the location of the point in 2D space, and y, the target feature, is the color. So we have blue and green here. So this is just kind of an abstract of what we talk about when we call concept drift. Concept drift is basically that one second. One second. Okay, right. Concept drift is I'll just start here. If the original data looks like this, what we say is, okay, that this line describes how we predict, it's the relationship of y given, y is the color, is given the location of the point. So this kind of squiggly line means that, okay, if x is over here, then it's green. If x is over here, then the y is blue. Okay. And distribution drift of x would mean like the points are in different locations. Like for example, here the points are kind of like uniformly, and here the points are in this area and this area, rather than everywhere, basically. So this is a case where the distribution of x changes because the x's are in different locations versus here, but the relationship of y based on x is unchanged because the rule for predicting the color based on location of x is unchanged. And here, so this is x changes, but not the p y given x. And then here is y given x changes. Notice that the points are in the same location, basically, as in the first picture, except the dividing line between the blue and the green changes, which means that the relationship between the predicted target and the x changes. So that would be, for example, this is like what we think of concept drift, where say perhaps the model, the machine learning model, has degraded between this image and this image because it no longer captures the true relationship between the target. And then this would be which they call virtual drift, would be like, for example, maybe the sampling changes, and that affects maybe the y's that you get, but only through, say, the fact that the underlying x has changed. So I guess an example here is yeah, okay, hold on. Does that kind of make sense? Again, the idea is that there's various types of drift, and you can decompose the drift as being of one or more causes, x or y, or y given x, or x given y, and they have various kinds of names, and unfortunately it's not very well defined. But again, the idea is that that I'll later discuss, is that usually you can use statistical tests to test either like the distribution of y or the distribution of x, and see which one has changed and kind of decide what is the responsible factor, basically. Okay, so again, I try not to be like math. I try not to introduce really mathematics other than the fact that you can decompose a distribution, but I'm not like talking about anything parametric really, just very abstract here. Okay. Yeah. Okay. And then here, there's this paper I just mentioned that kind of tries to formulate the various types of uh, tries to give like more formal names for the different types of drift that can happen because of various changes, depending on were the observations first sampled by X and then you got Y, or were they both sampled together? All kinds of uh, instances like that. Um, okay, so that's the main idea. Okay, and then here I tried to go into actually statistically how do you test these. So again, say that we have two data sets, D and D prime, and then you have these joint distributions P and P prime. Um, the basic idea in statistics is that okay, is that when you have you have a data set and you have a sample and from the data set, and that's supposed to represent some kind of population. So um, so um, what we actually see in the data set is a random sample from a population. Say, for example, okay, so initially I gave examples that these might represent each point is like a loan applicant, and this is one feature, and this is another feature, the age and the credit rating, and the color was whether they got a loan or not. Um, so uh, so for example, uh, maybe we have a thousand, the data set has 1,000, but really there's, you know, okay, so for example, uh, if these are all people from, Americans or something, but we only have a sample of 1,000, really, we don't just care about this sample. We want to make some kind of inference about the population, say like all Americans, for example, that these samples represent. So that's really what we're trying to test. So there's like a population distribution, capital P, as opposed to like these lowercase sample distributions, P and P prime. So really we want to know whether the capital P and P prime are different and not the sample distributions lowercase and P and P prime. And basically, again, this is just kind of statistics notation, but when you have a sample, you say like the P in the data set is an estimate, that's the hat here, of the population distribution capital P. And that's generally true. Right. So again, we're trying to decide based on these samples, how likely is it that the population distributions are the same or not? Okay, and that's basically drift. If the distributions are different, then that's some kind of drift. And usually what we're gonna do is what I said, two sample tests. You have a sample of the first sample, the baseline, and then the second sample, P prime, and you want to compare them as opposed to, for example, like a standard t-test calculates whether when you have a sample whether the mean is 0 or some other fixed numbers. That's a sample relative to a baseline as opposed to comparing two samples to each other. That's the difference here. And yeah. And any questions so far?
Um, one question, can you explain a bit how do I handle or how do I understand whether Okay, so I found a drift that has to do with the distribution, but I'm interested in drift in the performance of the machine learning model. How
Oh,
do I
yes. Right. So,
bridge the gap?
yeah, right. So thank you. So, uh, the way that we deal with that is again through the sample. So I'm getting that, but I guess I'll preface it. You can detect changes in distribution of sorry distribution changes in the performance, say of a machine learning model by similarly applying a the appropriate two sample test. So basically, if we have the data X and okay, so there's univariate tests and there's multivariate tests. A multivariate test will usually be on the data X if it has more than one feature. And univariate tests can be used on the target Y, or if X has a single feature, then on that. So in that case, usually the performance metric will be univariate. For example, you may know you might have a binary indicator whether the prediction is true or not, or for example, maybe you can measure the the squared error from of the of the predicted value from the true value, and then maybe that's a sample, and then you can compare that to maybe what you had on your training sample, and see if the distribution, so that maybe if the distribution of those changes versus say that again the fraction, if it's a binary, then basically you're testing is the average is the proportion of times that I make a mistake or not changing. And that, again, that would be a one sample, sorry, a two sample univariate test. And particularly, you might want to use a specific test where the data are binary rather than, say, continuous. Does that answer your question?
Yes, so it's like a two-stage game. One stage I identify that it's that there's a drift, and then another stage. Is that
Well,
true?
I think usually when you're testing drift, you have some kind of idea of what you're trying to test for. So if it's
Mhm.
performance, I mean, obviously you can test for multiple things at the same time, but in a given test, you would apply it on, say, again, in performance, it would be maybe, like I said, the binary indicator of whether it's correct or not, and then you would have a sample of values before and after, and then see,
Oh,
if
so
the
you mean
proportion.
it's around the statistics that interests me.
Yes, yeah, that's what I meant.
Okay. I see. I see.
And yeah, and then also later in the chapter, again, there's several different levels. Right now, I'm only dealing with a situation where we have a base, or like a baseline and a one observed set that's the D prime, which may be drifted or not. Later on in the chapter, I talk about like kind of a sequential monitoring where you have, say, a sequence of values, and then you can test has that changed overall. So for example, there's a test if like this, if you have a sequence of if you have a sequence of, say, binary indicators of correct or not correct that you're monitoring over time, you can test whether the distribution seems to change over time, by having like a moving window or something like that. That's
Great.
usually what's done.
So there's a methodological stage in which I choose the statistic I'm interested in because I'm interested in something specific, and then all of the techniques that you describe here will apply to that choice.
Yeah. Yeah, maybe I could right. Right. So yeah, so I started off kind of saying that before I start about performance is discussed later, but initially I'm just trying to test whether the distribution of the data changes.
Mm. Yeah.
Yeah.
Um,
Thank you.
thank you.
Any other questions or? No. Okay, so I'll just kind of like start to go over this, I guess. So again, which test you would use depends on what you're trying to test. So if it's like I said, if it's a univariate test is on something that is like a single variable, either x or the target y, and y could again be either continuous or discrete. And then multivariate you would generally use on x if it's multivariate. So the univariate tests are obviously the simplest one. Um, and sometimes there's several flavors of them. So sometimes you're trying to test whether, again, you have D and D prime, so two data sets. Again, these can either be the X's or the Y's themselves. So either you're trying to test some specific attribute of the distribution, say whether the average value or the median value or the variance has changed, as opposed to whether the whole distribution has changed. For example, you could have a case where the mean, where the distributions have changed, but the average value hasn't changed or haven't changed significantly. So for example, here, if you have a teacher and she is giving a test, okay, so you might want to know, has the average score on the test increased, relative to the first test, right? The first, math test or whatever. Uh, Regardless of whether the distribution has changed. So it might have been in the first test, maybe all the students got between a 70 and an 80, but the average was 75. But on the second test, the average was still 75, but they got between a 60 and a 90, or 60 and a 85 or something like that, or 90, right? So it can depend. In that case, the variance would be higher, but not, maybe the average didn't change. Again, this is just kind of an ideal situation. So okay, so for example, if you're interested in the average, there's the t-test, which is again two sample. There's several other tests. T-test is usually if it's normally distributed. Bartlett's, or there's several other tests like this, Bartlett's or Levine's test. If these are for differences in variance, but not the average. The Kruskal-Wallis is a test for the equality of means. And then if X are binary, again, or if you're testing, I should specify, if you're testing also on the target and that's binary, then you could basically you're testing for difference in proportions, and then there's like one of the tests is called Yates difference in proportions. And again, the difference is, for example, proportions can only be between 0 and 1, and they can't be, they're not real valued other than, outside of that. So you made a different test that takes that into account. Okay, guys, so notice usually throughout the test, I'm not like giving the mathematical details and just mentioning which tests are appropriate in which scenarios. And kind of giving the idea, but not the mathematical details. Let's see. Okay, so here's I guess the last thing I'll mention here is
Sam, for today's meeting, like another 2 to 5 minutes, and then we'll continue next time. Okay?
Sure. Right. Okay, so the things I just mentioned were if you're interested in testing the average, like a particular characteristic, if you just want to know the overall likelihood that these two distributions are the same or not, kind of you're trying to compare the whole distribution against each other. So there's usually in this chapter I kind of advocate non-parametric tests, because making parametric distributions are kind of can be problematic and gets harder if you have like multiple, it's multivariate. So some of these common tests are Kramer von Mises, Kolmogorov Smirnov, Anderson Darling. here's this test, Mann-Whitney U-test is, for example, are the not the distributions themselves the values, but rather the orderings, are they the same? Are they similar? So basically, this you would use if you want to know whether kind of two distributions overlap significantly, but not necessarily that they're the same distribution. So for example, say here's like a kind of standard scenario. If these two data sets are two racing teams, okay, and the values are the time in minutes that a racer finishes the race, okay. In a race, you typically the winners are maybe you get a point for, you know, the first place gets, or I guess the first place gets 10 points, the second place gets 9 points, and so on. In that case, it matters like only what order you're in, and not how much the first place winner beat the second place winner. So in this case, this basically to test whether these two teams were significantly were seen to be ranking the same means like if I kind of like interlace the times, would they be overlapped a lot, as opposed to a lot of one team being faster than most of the other members of other teams. So that's a case when you would use this test as opposed to, say, the t-test. Okay, that's probably all I have time for. But again, the point is you would try to give a sense of when you would use different tests in different scenarios.
And I say that you can, all of these tests are implemented right in in standard libraries.
Yeah, right. So I tried to cite where like usually Python, and try to focus on the ones that actually also have implementations, because otherwise it's just a theoretical exercise. Yeah. Again, the point is for this to be useful for someone who can actually like perform a test.
Great. This is great. Thank you. And we'll continue, of course. We'll go over the entire chapter. That's the plan here. And any additional questions to Sam for today?
Yeah.
Anyone?
You can also feel free to like Slack me or.
Yeah. Okay. Thank you very much, and we'll continue next week.
Okay. Thank you, Etan.
Bye-bye.
Bye bye.